Welcome back to 8701. So we switch gear now and talk about quantum electrodynamics, QED. And we'll start the discussion by going back to free wave equations. Now, you could argue that we are interested in collisions and we are interested in decays of particles, so why do we discuss free wave equations? Now, the theory we discussed last week, which we used in order to get a hold on Feynman diagrams and calculations, was very simplified. And one of the aspects not considered in this theory was the fact that particles carry spin. So we had a theory which only was applicable to scalars. Now, by walking through wave equations, we can see how we can incorporate or make use of the fact that particles actually do carry spin. So let's do this one by one. So we start off with our relativistic energy momentum relation. E square is equal to P square plus M square. We express energy and momentum via quantum mechanical operators. And so immediately by putting this in, we find this equation here, which is the so-called Klein-Gordon wave equation. So good. So if you look at this equation, we see that the second derivative here in time, there's no derivative in space. So there's an asymmetry between space and time. And that is not a really useful feature of our wave equation as we want them to be Lorentz invariant, for example. So what we want is a first order equation in both derivatives. So we'll just start writing this down in general terms and then make sure that this equation holds to the relativistic equation we just saw on the previous slide. We'll just write this down here. We have a first derivative time and a first derivative of space. And we just say there's a constant between those two, relating those two. So those sigmas are just unknown constants. So if you now try to find, by squaring this, try to find the Klein-Gordon equation and relate the coefficients, you find this relationship here. So the sigma square are all the same and equal to 1. But you also see that the sigmas, they anti-commutate, which is not possible for numbers. So sigmas need to be matrices. You also see that this is only holding true here for m equal to 0. So this equation here is true for a massless particle. All right, so if we then try to find solutions for those relations, we find that they can be fulfilled by the 2x2 Pauli matrices. We might have seen this already in a discussion of, hopefully have seen this in the discussion of atomic physics. And there, those Pauli matrices associate spin to electrons. So this is exactly what we have in mind here also. Now, using this definition, we can rewrite the Weyl equations to energy times the field is equal to minus sigma times the momentum times the field. And we find a second equation where just the sign flips. Those, the chi here and the phi are spinors. They are two-dimensional vectors. And the sigmas are our Pauli matrices. Good. So we have the relation now defined. But we can go a step further. Now, we want to introduce a mass term as well. I said that those hold for massless particles, so we want to introduce masses. So we can rewrite this equation and introduce this mass term here again with a coefficient. And we find now this alpha here being, so this phi here is a 4-component spinor, and it stands for the particle, its antiparticle, and the two spin states. So that's combining those two equations we had here. You will see one is for particles and one is for antiparticles for the two spin states. So we combine this in one equation and we added this mass term. So if you try to find the solutions here, you find that alpha is a matrix, 4x4 matrix, which has the sigmas, the Pauli matrices, on the off-diagonal elements. And beta is a diagonal matrix, 4x4 matrix with identity on the upper two components and -1 in the lower two components. So now with this, this is already the Dirac equation. We can rewrite the Dirac equation in a covariant form where you have just defined a new matrix here, so-called gamma matrix, which you build out of this matrix beta and alpha, which are defined on the previous slide. Good. So good. So we have this new matrix, this new equation here, which is the Dirac equation, and it holds for particles with two spin states, for example, spin half states, and there it holds for particles which have masses. So that's great. So this is now our starting point for the discussion. The next lecture will look at solutions of this equation.